What if everything we think we know about the universe is built on ideas that time forgot? Picture this: long before telescopes peered into deep space or equations unlocked the secrets of gravity, humanity gazed at the stars and dreamed up explanations so bold, so strange, they'd make modern science pause. Some were brilliant, others, well, let's just say they prove imagination has no limits when faced with the infinite unknown. Today, we're dusting off the pages of history to uncover 25 forgotten theories that once dared to explain the cosmos. These aren't just footnotes in a textbook, they're proof of our unshakable thirst to solve the universe's greatest mysteries, even when the answers were light years ahead of the tools we had. Think about the audacity it took for ancient stargazers to look up at the night sky and declare, "This is how it all works," without a single satellite or supercomputer to back them up. Some theories wove the cosmos into elaborate myths, where gods hurled lightning from celestial chariots. Others proposed invisible forces or hidden dimensions, ideas so ahead of their time they were laughed at until science caught up centuries later. What's truly wild, many of these discarded ideas planted the seeds for breakthroughs we now take for granted. The line between crazy and genius is thinner than we think, and every wrong turn in the dark still lit the way forward. So why revisit these cosmic dead ends? Because buried in their flaws are flashes of brilliance and reminders that even today's facts might one day seem just as quaint. This journey isn't just about bizarre guesses, it's about the human spirit's refusal to accept "we don't know" as a final answer. From fiery hollow Earths to living universes humming with consciousness, prepare to meet the theories that dared to redefine reality. Some will make you laugh, others might just make you wonder what if they weren't entirely wrong. The universe has always been stranger than fiction. And the best part, we're just getting started. Imagine a time when the universe wasn't a vast expanse of galaxies but something far more intimate, a single, shimmering egg waiting to crack open and spill out reality itself. This wasn't just one culture's whimsical idea, it was a thread woven through ancient civilizations, each painting their own version of the cosmic egg. In Hindu tradition, the Rigveda describes Hiranyagarbha, the golden womb from which Brahma emerged to shape existence. The Egyptians envisioned Ra, the sun god, bursting forth from an egg laid by the celestial goose Geb. Even the Orphic myths of Greece spoke of Phanes, the primordial deity hatched from a silver egg crafted by Kronos, the god of time. What's striking isn't just the imagery, it's the eerie consistency. Separated by continents and centuries, these cultures landed on the same metaphor: creation as a fragile, sacred moment of birth. Was it coincidence, or did they glimpse something fundamental about the universe's origins? Modern cosmology might dismiss the egg as mythology, but think about it: the Big Bang Theory, our leading scientific explanation, describes a singularity, an infinitely dense point that hatched into everything we know. The parallels are hard to ignore. Maybe these ancient storytellers weren't so far off. Without telescopes or particle accelerators, they observed the cycles of life, eggs giving rise to birds, seeds sprouting into trees, and saw a pattern they applied to the cosmos itself. It's a reminder that science and myth often ask the same questions, just with different tools. The cosmic egg wasn't just a pretty story, it was humanity's first attempt to answer the ultimate question: where did it all begin? And in that shared wonder across time and culture, we find something timeless: the audacity to imagine the unimaginable. What if you could dig straight through the ground beneath your feet and emerge into a world of eternal daylight? where an inner sun bathes lush landscapes in perpetual warmth. That's the tantalizing promise of the hollow Earth hypothesis, a theory so audacious it captivated scientists, adventurers, and storytellers for centuries. The idea didn't spring from fantasy alone. It was championed by none other than Edmund Halley, the same astronomer who calculated the orbit of Halley's comet. In the late 1600s, he puzzled over anomalies in Earth's magnetic field and proposed a radical solution. Our planet wasn't solid at all. Instead, he envisioned it as a series of nested spheres, like a cosmic Russian doll, each layer separated by atmospheres and possibly even hosting life. At the center, a glowing core, a miniature sun sustaining civilizations hidden beneath our feet. Halley wasn't alone in his fascination. Centuries later, the theory took on new life in the pages of Jules Verne's Journey to the Center of the Earth, where explorers descended through volcanic tunnels into a subterranean world of glowing mushrooms and prehistoric creatures. Verne's fiction tapped into something primal, the allure of the unexplored, the possibility that just beyond the edges of our maps lay wonders defying imagination. But here's where it gets even stranger. People didn't just read about it, they went looking. In the 1930s, Nazi-backed expeditions allegedly scoured the Arctic for entrances to this inner realm, and even today, pockets of true believers claim hidden passages exist in places like Mount Shasta or the Amazon rainforest. Science, of course, has long since debunked the idea. Seismic waves reveal Earth's layered interior, and gravity measurements confirm it's overwhelmingly solid. Yet the theory's endurance speaks volumes. It's not just about geology, it's about the human itch to peel back layers, to believe there's always another mystery waiting beneath the surface. The hollow Earth is a mirror reflecting our deepest curiosity. If the universe feels too vast to grasp, maybe the answers are closer than we think, buried right under our feet. And who's to say that spirit of exploration, however misguided, didn't pave the way for real discoveries? After all, every dismissed idea reminds us that today's impossible might be tomorrow's breakthrough. So the next time you stare at the ground, remember, even the wildest theories carry a spark of something timeless, the refusal to accept that anywhere, even deep below, is truly off limits. The universe had always existed, no fiery beginning, no dramatic collapse, just an endless cosmic dance where matter quietly appeared to fill the void as space stretched outward. This was the elegant promise of the steady-state theory, a bold challenge to the idea of creation itself. In the 1940s, as astronomers first grappled with evidence of an expanding universe, most assumed it meant everything had erupted from a single point. But three scientists, Fred Hoyle, Thomas Gold, and Hermann Bondi, proposed something radically different. What if the universe simply was unchanging in its overall density, with new atoms continuously popping into existence to maintain perfect equilibrium? No messy singularities, no unanswered questions about what came before, just an infinite, self-renewing cosmos. Hoyle, the theory's most vocal champion, famously mocked the rival idea as the Big Bang, a nickname meant to sound absurd. Yet irony struck when the label stuck, eclipsing his own vision. The steady-state model wasn't without merit, though. It neatly sidestepped the philosophical headache of a cosmic beginning, offering a universe that required no creator or cataclysm. To many, that was deeply appealing. Even Einstein had balked at the idea of a dynamic universe, initially tweaking his equations to preserve eternal stillness. The steady-state theory felt like a return to that classical comfort, a universe without birth or death, where time stretched endlessly in both directions. But science thrives on evidence, not comfort. The theory's downfall came in the 1960s with the accidental discovery of cosmic microwave background radiation, the faint afterglow of the Big Bang. Here was the smoking gun. The universe had a fiery infancy, and the steady state couldn't explain it. Yet Hoyle, ever the contrarian, refused to concede, tweaking his model until the end. His stubbornness wasn't just pride, it underscored a deeper tension in science. We crave stability, patterns, rules, and the steady state offered that in spades. The Big Bang, by contrast, forced us to confront chaos, impermanence, and the unnerving truth that even the universe had a birthday. What's fascinating isn't just that the theory was wrong, but why it persisted. Before modern telescopes, an eternal universe seemed simpler, more rational. It mirrored the steady rhythms of daily life, seasons cycling, stars rising, a world without end. The steady state was science's last stand against cosmic impermanence, a final attempt to keep the universe familiar, and in its defeat, we learned something profound. Reality doesn't bend to our longing for order. Sometimes the truth is stranger, wilder, and more beautiful than even the most elegant theories dare to imagine. What if the force holding galaxies together wasn't gravity at all, but something far more familiar, something crackling through the wires in your walls right now? The electric universe theory turns conventional cosmology on its head, proposing that electricity, not gravity, is the invisible hand shaping the cosmos. Picture this: vast rivers of charged particles called plasma, weaving between stars like cosmic power lines, sculpting nebulae into glowing filaments and spinning galaxies into existence. Proponents argue that if you've ever seen plasma bend into intricate shapes in a lab, those eerie, twisting tendrils of light, you've glimpsed the universe's true blueprint. The idea isn't entirely pulled from thin air. In the mid-20th century, physicist Hans Alfvén won a Nobel Prize for his work on magnetohydrodynamics, showing how plasma's electromagnetic properties could influence celestial structures. His research hinted that electricity might play a bigger role in space than we'd assumed. Electric universe theorists took this further, suggesting that everything from solar flares to galaxy formation could be driven by colossal electric currents. They even reinterpret ancient myths about thunderbolts from the gods as early human encounters with cosmic electrical storms. Mainstream science, of course, remains skeptical. Gravity's dominance is backed by mountains of evidence, from the orbits of planets to the bending of light around black holes. Yet the electric universe crowd raises provocative questions. Why do some cosmic structures, like the mysterious filaments stretching between galaxies, resemble the branching patterns of lightning? Could electromagnetism explain anomalies that gravity alone struggles with? Even if the theory's grand claims falter, it forces us to re-examine assumptions, and that's where its real power lies. History shows that dismissed ideas often contain kernels of truth. Galileo's telescopes were once ridiculed, continental drift was mocked for decades. While the electric universe likely isn't the final answer, its boldness reminds us that science thrives on dissent. Maybe plasma does more in space than we've accounted for. Maybe future discoveries will blend electromagnetic and gravitational models into something entirely new. For now, the theory stands as a lightning rod, challenging us to question whether we've truly grasped all the forces at work in the dark expanse above. After all, the universe rarely fits neatly into the boxes we build for it, and sometimes the most electrifying ideas are the ones that jolt us out of complacency. Long before we understood nuclear fusion, before telescopes could dissect starlight into elemental fingerprints, there was phlogiston, an invisible substance that seemed to explain why things burned. 18th century chemists watched flames dance and reasoned that fire wasn't a reaction but a release, as if every combustible material secretly housed this elusive fire element. When a log crackled in the hearth, they believed phlogiston was escaping, leaving behind ash like a ghost slipping out of its body. But the theory didn't stop at Earth's surface. Starry-eyed thinkers stretched the idea to the heavens, proposing that the sun and stars were celestial furnaces, blazing with phlogiston as they hung suspended in the void. It's easy to smirk now, knowing stars run on hydrogen fusing into helium under crushing gravity, a process so violent it makes earthly fires look like birthday candles. Yet phlogiston's appeal was undeniable. For the first time, it linked earthly chemistry to the cosmos, suggesting a universal rule governing flames in both hearths and heavens. Even the great Antoine Lavoisier, who later debunked the theory, initially toyed with the idea, but cracks soon appeared. If phlogiston was lost during burning, why did some metals gain weight when heated? The theory's unraveling began with these quiet contradictions, until oxygen's discovery lit the way to modern chemistry. What's remarkable isn't just that phlogiston was wrong, it's how wrongness can still light the path forward. The very experiments designed to prove phlogiston's existence, like meticulous weighings of burnt metals, became the bedrock of Lavoisier's new chemistry. In a way, phlogiston was a placeholder, a conceptual scaffold holding up early science until stronger evidence could take its place. And that's the hidden lesson. Every discarded theory is a stepping stone, not a dead end. Look up at the night sky today, and you're seeing it through centuries of such missteps and corrections. We now know stars as nuclear reactors, not phlogiston bonfires, but who's to say our current models won't seem just as charmingly naive to future astronomers? Maybe dark matter will turn out to be the phlogiston of our age, a clumsy label for something we don't yet grasp. The universe has a habit of humbling our certainty, and that's what makes science thrilling. It's not about being right from the start. It's about daring to guess, testing boldly, and letting even the wildest ideas burn bright until they're refined or replaced by something brighter still. The universe is expanding, or at least, that's what every astronomy textbook tells us. But what if redshift, the key piece of evidence for cosmic expansion, wasn't about galaxies racing away at all? In 1929, Fritz Zwicky, the same maverick astronomer who coined the term supernova, threw a wrench into cosmology with his tired light hypothesis. He proposed a radical alternative. Maybe light itself grows weary, shedding energy like a marathon runner losing steam over vast distances. The farther it travels, the more stretched out or redshifted it becomes, mimicking the illusion of an expanding universe without any actual motion. Zwicky wasn't just stirring the pot for fun. His idea tackled a genuine puzzle. If light could lose energy through interactions with interstellar dust or even some unknown property of space itself, it would neatly explain redshift without invoking a runaway cosmos. The elegance of the theory lay in its simplicity. No need for a mysterious Big Bang or dark energy, just light, slowly fading over its epic journey. For a moment, it seemed like a plausible challenger to the fledgling expansion model. But science doesn't settle for plausible. It demands proof. The cracks in Zwicky's hypothesis appeared when astronomers noticed that redshift wasn't the only cosmic fingerprint of expansion. Distant supernova dimmed in ways that tired light couldn't explain, and the cosmic microwave background's precise spectrum matched predictions of an explosive origin. Most damning, if light truly tired, distant galaxies should appear blurrier than they do, as scattered photons smeared their images. Yet telescopes revealed crisp, sharp shapes even at the edge of the observable universe. So why does this failed theory matter? because Zwicky's stubbornness forced cosmologists to sharpen their arguments. Every critique of tired light became a brick in the foundation of Big Bang cosmology. It's a pattern we've seen again and again. The most enduring scientific models aren't just born from evidence, but from surviving relentless challenges. And here's the twist: while tired light itself may be defunct, its spirit lingers. Modern physicists still grapple with photon decay, the idea that light might lose energy over unimaginable timescales. Even wrong theories plant seeds. Zwicky's legacy isn't just a cautionary tale, it's a celebration of science's self-correcting nature. The next time you hear about a crazy alternative to mainstream cosmology, remember, today's fringe idea might be tomorrow's missing puzzle piece. After all, the universe rarely reveals its secrets to those who never dare to question the obvious. And sometimes, the boldest wrong answers lead us to the most profound truths. Atoms as tiny tornadoes, that was the dazzling vision of Lord Kelvin in the late 1800s, a time when the true nature of matter was still shrouded in mystery. Picture the universe filled with an invisible fluid, the luminiferous ether, and within it, atoms weren't solid dots but dynamic whirlpools, spinning endlessly like cosmic eddies. Kelvin's Vortex theory of atoms wasn't just poetic, it was a mathematical masterpiece. He calculated that these ethereal vortices could knot and link like smoke rings, their stability explaining why atoms of different elements had distinct properties. Iron's vortex might tangle differently from hydrogen's, giving each element its unique character. And here's the wildest part: this Victorian-era idea accidentally brushed against truths quantum physics wouldn't uncover for decades. The way Kelvin's vortices interacted hinted at quantization, a property central to modern atomic theory. But why did such an elegant model fade into obscurity? The ether itself was the theory's Achilles heel. When experiments like Michelson and Morley's failed to detect this mysterious medium, the foundation crumbled. Quantum mechanics stepped in, painting atoms as probability clouds orbiting nuclei, a far cry from Kelvin's graceful whirlwinds. Yet to dismiss vortex theory as a dead end misses the point. It was a triumph of imagination, a reminder that even wrong ideas can sharpen the questions that lead to breakthroughs. Kelvin's vortices didn't just inspire physicists, they influenced mathematicians studying knot theory, a field now vital in everything from DNA research to quantum computing. So what's the lesson for today's cutting-edge theories? Look at string theory with its tiny, vibrating filaments replacing point-like particles, or loop quantum gravity, where space itself is woven from interconnected loops. Both are unproven, both are beautiful, and both might be the vortex atoms of our era, destined to be overturned but still guiding us closer to reality. Science doesn't march in a straight line. It spirals, twists, and occasionally doubles back, with every wrong turn illuminating the path forward. The next time you hear a far-out idea about the fabric of the universe, remember, today's dismissed vortex could be tomorrow's revolution. After all, the history of science isn't just a record of answers, it's a testament to the power of asking bold, beautiful questions. The night sky wasn't just a scattering of stars to the ancient Greeks, it was a masterpiece of celestial engineering, each planet mounted on its own transparent sphere, rotating with perfect harmony like gears in a divine machine. This was the cosmology of crystal spheres, a vision so precise it governed astronomy for nearly 2,000 years. Picture it, Earth at the center, encased in nested orbs of pure celestial glass, each carrying the moon, the sun, or a wandering planet in flawless circular motion. The spheres didn't just explain the heavens, they ordered them, turning chaos into geometry. And when Claudius Ptolemy refined the model in the 2nd century, adding epicycles, tiny loops within loops to account for retrograde motion, it became a mathematical marvel, predicting planetary positions with uncanny accuracy. What's astonishing isn't just that the model was wrong, but how right it managed to be with no telescopes, no calculus, just naked eye observations and sheer ingenuity. For centuries, sailors, farmers, and kings relied on Ptolemy's tables to navigate seasons and eclipses. The theory's real genius lay in its flexibility. Each new astronomical anomaly could be fixed by adding another epicycle, another tweak to the cosmic clockwork. It was science as puzzle solving, a reminder that even flawed frameworks can push knowledge forward when they are all we have. Then came Copernicus with a single radical premise. What if the sun, not Earth, was the center, the crystal spheres shattered? Kepler's ellipses and Newton's gravity finished the job, reducing Ptolemy's intricate dance to a beautiful relic. Yet here's the twist: the spheres weren't entirely useless. Their insistence on mathematical precision set a standard for future astronomers. Without Ptolemy's obsession with predicting Venus's path, would Tycho Brahe have spent decades refining his star maps? Would Kepler have discovered his laws? Even wrong models can be stepping stones, training wheels for the scientific method itself. So why does this matter today? Because every time we scoff at ancient mistakes, we risk forgetting how much they taught us. Modern cosmology has its own crystal spheres, dark matter, string theory, multiverses, ideas we cling to because they almost explain what we see. Will they seem just as quaint to astronomers 1,000 years from now? Probably, and that's the point. Science isn't about being right forever, it's about being less wrong over time. The crystal spheres remind us that today's cutting-edge theories are tomorrow's historical footnotes, and that's not a flaw. It's how we inch closer to the truth, one shattered assumption at a time. Picture a world where the ground beneath your feet isn't just shifting, it's stretching, swelling, pushing continents apart like cracks in a slowly inflating balloon. This was the expanding Earth theory, a mid-20th century idea that dared to rewrite geology's rules. Before plate tectonics became the cornerstone of modern Earth science, a handful of renegade researchers proposed something wild. Maybe the continents weren't drifting on molten currents, but riding atop a planet that was literally growing. The evidence seemed compelling at first glance. Look at a map, and the coastlines of Africa and South America fit together like puzzle pieces, but what if they weren't torn apart by shifting plates? What if the Atlantic Ocean was just the gap left behind as Earth expanded, its surface crust stretching thin like rubber over an ever larger core? The theory's boldest champion, German geologist Otto Hilgenberg, even built intricate models to show how today's continents could perfectly cover a smaller, ancient Earth. His vision was poetic in its simplicity. No need for subduction zones or mantle convection, just a planet inhaling cosmic material swelling over eons. And for a brief moment, it wasn't entirely fringe. Even the legendary astronomer Fred Hoyle flirted with the idea, suggesting that new matter might be bubbling up from Earth's core. The theory's appeal lay in its ability to explain so much with so little continental drift without the messy mechanics of plate tectonics. But science, as always, demanded proof. By the 1960s, seismic data revealed Earth's interior with unprecedented clarity, showing slabs of crust plunging back into the mantle, something an expanding planet couldn't explain. Satellite measurements confirmed it. Earth wasn't changing size. Yet here's where the story gets fascinating. While our planet might not be growing, some worlds are. Saturn's moon Enceladus, for instance, has an icy shell that expands and contracts as underground oceans freeze and thaw. Jupiter's volcanic moon Io heats up so much from tidal forces that it might actually puff up over time. The expanding Earth theory wasn't just wrong, It was locally wrong, a solution that fit the wrong cosmic neighborhood. What's truly humbling is how easily the human mind conflates correlation with causation. Those matching coastlines did hint at a deeper truth, just not the one Hilgenberg imagined. And that's the real lesson here. Right now, astronomers stare at redshifted galaxies and assume universal expansion. Physicists hunt for dark matter to explain gravitational anomalies. But what if we're making another Hilgenberg-style leap, mistaking a shadow on the wall for the shape of the thing itself? The universe specializes in humble pies, serving them up whenever we grow too confident in our models. The expanding Earth theory isn't just a cautionary tale. It's an invitation to stay curious, to question even the explanations that seem to fit perfectly. Because sometimes the truth isn't just hidden, it's waiting for us to outgrow our assumptions. The surface of Mars was alive, or at least that's what Percival Lowell swore he saw through his telescope in the late 1800s. Dark, straight lines crisscrossed the red planet like a meticulously planned irrigation network, and to Lowell, there was only one possible explanation: intelligent Martians had built them. His sketches of these canals became a sensation, fueling a wave of speculation about an ancient civilization clinging to survival on a dying world. Newspapers ran headlines about Martian engineers, and science fiction authors like H.G. Wells spun tales of invaders from the Red Planet. For decades, the idea wasn't just fringe fantasy. It was a legitimate scientific hypothesis, championed by a respected astronomer with a state-of-the-art observatory at his disposal. But here's the twist: those canals didn't exist. Modern telescopes and space probes revealed Mars as a barren, windswept desert, its surface scarred by canyons and dust storms, no straight lines, no alien aqueducts. So what was Lowell really seeing? The culprit was a mix of optical illusion and human psychology. When peering through the blur of Earth's atmosphere, the brain instinctively connects faint, irregular patches into familiar patterns, just like seeing shapes in cloud. Lowell's canals were the cosmic equivalent of a mirage, a trick of the mind as much as the eye. Yet for all its wrongness, the canal theory left an indelible mark on science. The public's fascination with Martian engineers fueled early rocketry experiments, with pioneers like Robert Goddard citing Lowell's work as inspiration. Even Carl Sagan admitted that the canals, though fictional, accelerated the exploration of Mars by decades. It's a strange irony, a mistake that propelled humanity forward. Which raises a tantalizing question: what illusions are we falling for today? Dark matter's gravitational fingerprints, the faint radio signals some claim as extraterrestrial transmissions. Science is littered with placeholders, ideas we cling to because they're the best we've got for now. The Martian canals remind us that even our most earnest observations can be warped by expectation, and that the line between discovery and delusion is often thinner than we think. The next great breakthrough might not come from confirming our hunches, but from daring to question them. After all, the universe has a way of humbling those who mistake their assumptions for answers. Copernicus dethroned Earth from the center of the universe in the 1500s, or so we thought. But like a cosmic game of whack-a-mole, geocentrism kept popping back up, even in the 20th century, armed with an unlikely ally: Einstein's theory of relativity. Here's the twist: relativity states that all motion is relative, meaning any point in space can technically be treated as stationary if you choose the right reference frame. A handful of contrarians seized on this, arguing that picking Earth as the fixed center wasn't scientifically invalid, just unconventional. After all, if the math works either way, why not let Earth keep its pride of place? But let's be clear, this wasn't a true return to Ptolemy's crystal spheres. Modern geocentrists weren't denying planets orbited the sun. they were exploiting a quirk of physics to argue that perspective is everything. In their models, the entire universe whirled around Earth in a dizzying ballet of spiraling galaxies, all to preserve our planet's centrality, the math. Surprisingly coherent, the practicality, a nightmare. Choosing Earth as the cosmic anchor meant rewriting celestial mechanics with needlessly convoluted equations, like describing a sunset by pretending the entire universe rotates daily. Possible, yes, useful, not even slightly. What's fascinating isn't the science, it's the psychology. Why would anyone cling to such an awkward reinterpretation of the cosmos? For some, it was religious conviction, for others, sheer contrarianism. But beneath it all lay a timeless human truth: we want to be special. Demoting Earth to just another planet felt like a demotion of us, a cosmic snub to human significance. And that instinct didn't die with Galileo. Today, we still grapple with versions of this bias: dark energy, multiverses, even the search for alien life. Each forces us to confront the unsettling idea that we might not be the universe's protagonists. So here's the real question. If geocentrism could dress itself in relativity's clothes, what outdated assumptions are we propping up with modern jargon? Every generation thinks it's shed the last of humanity's cosmic vanity, only to find new ways to center itself in the story. Maybe that's the ultimate lesson of the geocentric comeback. No matter how far our telescopes peer, the hardest thing to see clearly is our own reflection in the glass. Light behaves like a wave. We've all seen the ripples in a pond or the undulating patterns of sound. So when 19th century physicists discovered light's wave-like nature, they faced a puzzle. Waves need something to wave through. Sound travels as vibrations in air, ocean waves ride atop water, but space was supposed to be empty, a vacuum devoid of substance. The solution: an invisible, intangible medium called the luminiferous ether, an all-pervading cosmic fabric through which light could ripple like whispers through a crowded room. This wasn't just some wild guess, it was a necessary conclusion based on the best science of the age. If light waves existed, so must their stage. The ether's proposed properties read like a recipe for the universe's most exotic material. It had to be frictionless to avoid slowing planets, yet rigid enough to transmit light's blistering speed. It was massless but somehow filled every crevice of space, even passing through solid matter like a ghost. For decades, physicists treated it as fact, crafting elaborate experiments to detect its presence. The most famous of these was the Michelson-Morley experiment in 1887, which aimed to measure Earth's motion through the ether like a ship cutting through water. The result: nothing. No ripple, no drag, no hint that the ether existed at all. It was as if the universe had erased its own footprints. Einstein's theory of relativity eventually rendered the ether obsolete, showing that light doesn't need a medium. It's a self-contained electromagnetic phenomenon. Yet the idea never fully vanished. Some theorists speculate that dark energy, the mysterious force accelerating the universe's expansion, might be a spiritual successor to the ether, an invisible, space-filling presence we can't directly see but whose effects are undeniable. Others draw parallels to quantum field theory, where space isn't truly empty but seething with virtual particles popping in and out of existence. In a way, we've come full circle, replacing the ether with something even stranger. What's remarkable isn't just how wrong the ether turned out to be, but how right it felt at the time. Science often progresses by building the best possible bridge between what we know and what we don't, even if that bridge leads nowhere in the end. The ether was that bridge, a placeholder for deeper truths waiting to be uncovered. And in its failure, it taught us something profound. Sometimes, the most elegant explanations are the ones that force us to abandon our intuitions completely. The universe doesn't owe us familiarity. It's under no obligation to make sense in ways we expect. So the next time you flip a light switch, remember, the glow illuminating your room isn't riding some invisible cosmic tide. It's a reminder that reality, when looked at closely, is far weirder than anything we could invent. Even Einstein, the man who reshaped our understanding of gravity, balked at the idea of black holes. He once wrote that while his equations suggested such objects might exist, nature would surely find a way to prevent them. It's a striking irony. The very theory that predicted black holes also had its creator doubting their reality. But this wasn't just stubbornness. It was a reflection of how deeply counterintuitive these cosmic monsters seemed. Imagine a place where gravity wins forever, where space and time twist into a knot so tight even light can't escape. To the greatest minds of the early 20th century, that didn't just sound unlikely, it sounded impossible. Long before Einstein, an English clergyman named John Michell had already toyed with the concept. In 1783, he envisioned dark stars, celestial bodies so massive their gravity would trap light itself. Michell's calculations were startlingly prescient, but without the tools to test them, the idea faded into obscurity. For over a century, black holes existed only as mathematical ghosts, lurking in the margins of theory. Even when Carl Schwarzschild solved Einstein's equations in 1916, revealing the possibility of infinitely dense points in space, most physicists dismissed them as quirks of the math, artifacts with no real-world counterpart. The resistance wasn't just scientific, it was almost philosophical. Black holes violated every instinct about how the universe should behave. Matter couldn't just vanish, space couldn't simply end, and yet here were these equations whispering otherwise. It took the stubbornness of thinkers like Subrahmanyan Chandrasekhar, who faced ridicule for calculating that dying stars could collapse into nothingness, and the observational genius of Jocelyn Bell, whose pulsar discoveries hinted at the extreme states of matter, to chip away at the skepticism. By the time Cygnus X1, the first confirmed black hole, was detected in 1971, the evidence was undeniable. But here's the haunting question buried in this history. What cosmic truths are we still refusing to see? Today, we face new paradoxes: white holes spewing matter into the universe, wormholes threading space-time, even holographic universes encoded on distant boundaries. Some of these ideas will prove prophetic, others will join Michell's dark stars as fascinating dead ends. The lesson isn't just that science corrects itself, but that it thrives on the tension between imagination and proof. Every radical idea, no matter how outlandish, forces us to ask, are we clinging to comfort, or are we brave enough to follow the math wherever it leads? The story of black holes isn't just about gravity's victory. It's about the human mind's slow, reluctant march toward the unimaginable. And somewhere out there, in the darkness we've yet to explore, the next great cosmic surprise is waiting, patient and silent, for our equations to catch up. What if time wasn't a straight arrow but a shape, something you could hold in your hands, turn over, and examine from every angle? That's the mind-bending premise of the time cube, a theory so bizarre it was once relegated to the fringes of the internet. In 1997, an inventor named Jean Ray began plastering the web with frantic manifestos declaring that time wasn't linear but cubic, a four-dimensional structure where every moment existed simultaneously across 4 distinct days within a single rotation. His diagrams looked like scribbled fever dreams, with cubes splitting into quadrants labeled morning, noon, evening, and night, each representing a different face of time. To mainstream science, it was gibberish, but buried in Ray's rambling prose was a provocative question. What if our perception of time as a straight line is just a shadow of something far more complex? Ray's cubic obsession wasn't entirely without precedent. Philosophers have long wrestled with time's true nature, whether it's a fundamental property of the universe or just a human construct. Even Einstein showed that time bends near massive objects, warping like taffy under gravity's pull. String theory takes it further, suggesting hidden dimensions where time might loop or braid in ways we can't perceive. Ray's mistake wasn't asking whether time could be multidimensional. It was insisting he'd solve the puzzle with a literal cube. Yet his rants struck a nerve precisely because they highlighted how little we truly grasp about time's architecture. Consider this: when you watch a sunset, your brain stitches together photons that left the sun 8 minutes ago with the sound of waves hitting the shore milliseconds earlier. Your now is already a patchwork of staggered inputs. Now imagine scaling that up. What if time's flow is just an illusion, a slice of a higher dimensional structure we're biologically unequipped to see? The time cube's real legacy isn't its geometry. It's the way it forces us to confront the limits of our intuition. After all, if a 19th century physicist had described quantum entanglement, where particles instantly influence each other across light years, they'd have been laughed out of the room. Today, it's textbook science, so here's the twist. While Ray's cube remains firmly in the realm of fringe cosmology, the questions it raises are anything but silly. Modern physicists toy with similar ideas, from Julian Barber's timeless universe to Carlo Rovelli's suggestion that time might emerge from quantum relationships. The line between crackpot and visionary is often just a matter of evidence and patience. Maybe time isn't a cube, but what if it's a spiral, a fractal, or a mosaic of moments we're only beginning to decode? The next time you glance at a clock, remember, the true nature of time might still be hiding in plain sight, waiting for someone bold enough to redraw the map. And sometimes it takes a theory as delightfully wrong as the time cube to remind us how much we have left to discover. The universe isn't just held together by gravity, it's electrified. That's the radical vision of Nobel laureate Hans Alfvén, who saw space not as a quiet vacuum but as a seething ocean of magnetized plasma, sculpting galaxies and birthing stars with currents we're only beginning to map. While his work on magnetohydrodynamics revolutionized our understanding of solar flares and Earth's auroras, Alfvén didn't stop there. He dreamed bigger, proposing that 99% of the cosmos wasn't made of stars or gas, but of plasma-charged particles dancing to the tune of electromagnetic forces. In his plasma universe, gravity played second fiddle to vast, invisible circuits arcing between celestial bodies, powering cosmic structures like a hidden electrical grid. Mainstream cosmologists balked. After all, gravity had Newton and Einstein on its side, their equations neatly explaining planetary orbits and the bending of starlight. But Alfvén's ideas weren't so easily dismissed. When spacecraft like Voyager later discovered filamentary structures in nebulae, threads of glowing plasma eerily similar to lab experiments, even skeptics paused. The sun's corona, hotter than its surface, defied gravity-based models until plasma physics stepped in. Alfvén's grand unified plasma universe might have been too extreme, but its fingerprints were everywhere. Here's where it gets fascinating. The line between fringe and foundational is often just a matter of time. Alfvén's insistence on plasma's role in space weather is now textbook science, guiding satellite designs and asteroid mining proposals. Modern astronomers study flux ropes of magnetic energy in galaxy clusters, structures Alfvén predicted decades ago. Even the mysterious fast radio bursts, those cosmic sirens from distant galaxies, are sometimes modeled as plasma-driven phenomena. The plasma universe didn't conquer cosmology, but it left an indelible mark, proving that even the boldest heresies can become tomorrow's orthodoxy if enough evidence piles up. So what's the lesson for today's cosmic mysteries? Dark matter's gravitational grip might dominate our models now, but could we be overlooking electromagnetic quirks lurking in plain sight? Elfvane's story reminds us that science advances when we question which forces we've overestimated and which we've underestimated. The universe doesn't care which theory wins, it just keeps humming along, full of surprises. And sometimes the most electrifying breakthroughs come from those willing to challenge the current. What if the entire universe is just one roll of the dice in an endless cosmic casino? That's the dizzying premise behind the infinite monkey theorem's leap from literary curiosity to cosmological speculation. Picture a room full of monkeys pounding away at typewriters for eternity. Given enough time, literally infinite time, they'd eventually produce the complete works of Shakespeare purely by chance. Now stretch that idea across the multiverse. If infinite parallel realities exist, doesn't that mean somewhere, against impossible odds, a universe like ours had to emerge with the perfect conditions for life? Suddenly, the fine-tuning of physics, the eerie precision of constants like gravity or the strength of atomic bonds isn't a mystery, it's statistical inevitability. This thought experiment isn't just playful philosophy, it taps into a genuine tension in modern physics. When cosmologists stare at the razor's-edge perfection of our universe's parameters, they grapple with two unsettling options. Either an untold number of failed universes exist beyond our view, the multiverse hypothesis, or some deeper principle, perhaps even a designer, set the dials just right. The monkey theorem leans hard into the first camp, framing our existence as a fluke so rare it only makes sense against a backdrop of infinite tries. And here's where it gets weirdly poetic. If true, we're not special. We're just the lucky monkeys who happen to type Hamlet. Critics pounce on the theory's slippery logic. Infinity isn't a magic wand, it's a conceptual quicksand. If every possible outcome must occur given infinite time, what about outcomes that defy probability altogether? Could monkeys also type out a flawless prediction of next year's stock market or a cure for cancer? The theorem brushes up against the difference between possible and meaningful. Our universe isn't just orderly, it's fruitful, generating complexity that builds on itself over billions of years. Randomness can explain a single sonnet, but can it explain sonnets that write themselves? Yet for all its flaws, the metaphor lingers because it mirrors a profound shift in how we see reality. Science has dethroned humanity from the center of the cosmos, the heart of the solar system, even the apex of evolution. Now it whispers a humbler truth. We might not even be the main event in our own universe, just one accidental arrangement in an endless sea of possibilities. That's the monkey theorem's real gift, not an answer, but a mirror. Stare into it long enough, and you start to wonder, is our search for cosmic meaning itself just another random keystroke in the dark? Or is there a pattern even infinity can't erase? The monkeys keep typing, the universe keeps expanding, and somewhere in the noise, we're left to decide whether our story is luck or something more. The moon isn't just a rock, it's a perfect cosmic coincidence, so perfect, in fact, that some swore it couldn't be natural. In the 1970s, a handful of scientists and conspiracy theorists looked up at Earth's closest companion and saw something stranger than cheese or craters, an ancient megastructure, possibly even an alien observation post. The hollow moon hypothesis wasn't just sci-fi fodder. It was a full-blown alternate history of the solar system, built on eerie lunar quirks. Why does the moon orbit at exactly the distance needed to perfectly eclipse the sun? How did Apollo seismometers pick up reverberations lasting hours after meteor strikes, as if the surface were ringing like a bell? And why do some lunar samples contain metals like brass, which typically require artificial refining? To believers, these weren't mysteries, they were clues. The theory's heyday coincided with the Apollo missions, which should have buried it for good. Instead, the more we learned, the weirder the moon seemed. When astronauts accidentally dropped a spent lunar module, the resulting vibrations lasted far longer than expected, fueling whispers of a hollow interior. Mainstream geologists pointed to the moon's fractured crust, which could amplify seismic waves, but the allure of the impossible stuck. Even Carl Sagan, ever the skeptic, entertained the idea in his book Intelligent Life in the Universe, suggesting advanced civilizations might build hollow worlds as interstellar arcs. The moon, of course, wasn't one of them, but the thought lingered. Science fiction seized the concept with glee, from Arthur C. Clarke's 2001 to modern shows like The X-Files. The hollow moon became a trope, a canvas for stories about hidden alien bases or dormant supercomputers. But here's the twist: the theory's persistence isn't just about aliens. It's about patterns seeking the same instinct that makes us see faces in clouds or hear hidden messages in music. When faced with cosmic oddities, our brains itch to explain, even if it means inventing architects for celestial bodies. The moon, so close yet so enigmatic, is a Rorschach test for our imaginations. So why does this idea still echo in pop culture, long after seismology and samples confirmed the moon's very solid, very natural origins? Because conspiracy theories aren't really about evidence. They're about storytelling, about turning the universe into a puzzle with us at the center. The hollow moon taps into a deeper anxiety. What if we're not the smartest beings in the room? What if the sky is full of artifacts we're too primitive to recognize? NASA laser reflectors and rover tracks haven't killed the myth. They've just forced it to adapt, mutating into new forms like the secret Nazi moon base, Sojourner. In the end, the hollow moon is more than a debunked hypothesis. It's a mirror reflecting our relationship with the unknown. Every generation projects its fears and fantasies onto the cosmos, dressing the void in whatever mythology feels most urgent. Today, it's ancient aliens. Tomorrow, who knows? But one thing's certain: as long as the moon hangs there, silent and scarred, we'll keep weaving tales about what or who might be lurking in its shadows. And maybe that's the real mystery, not whether the moon is hollow, but why we so desperately want it to be. Black holes devour everything in their path, but what if the universe has a way of giving back? Enter white holes, the theoretical opposites of their dark cousins. While black holes trap matter and light in an inescapable grip, white holes would violently expel them, spewing out energy and particles like a cosmic fire hose. The math allows for their existence, emerging as mirror image solutions to Einstein's equations of general relativity. Yet, unlike black holes, which we've now photographed and studied, white holes remain stubbornly hypothetical, ghosts in the machinery of the cosmos. The idea isn't just a playful thought experiment. Some physicists speculate that if a black hole's crushing singularity leads to a tunnel through space-time, a wormhole, then the other end might just be a white hole, violently birthing matter into another universe. Even wilder is the notion that our own Big Bang could have been a white hole event, the explosive release of pent-up energy from some distant, collapsing reality. Picture it, not a singularity bursting from nothing, but a cosmic overflow valve, recycling material from a universe that came before. It's a tantalizing alternative to the idea of creation from absolute emptiness. But why haven't we seen one? If white holes exist, they'd be hard to miss, blazing with energy as they fling out matter at unimaginable speeds. One explanation is that they're incredibly short-lived, collapsing almost instantly under the weight of their own outbursts. Another possibility: they're hiding in plain sight. Some theorists suggest gamma-ray bursts, those brilliant, mysterious flashes in deep space, could be the dying gasps of white holes, their final eruptions before winking out of existence. The real allure of white holes isn't just their strangeness, it's what they represent. They challenge our assumptions about cause and effect, about the one-way flow of time. If black holes are the universe's drains, white holes hint at something far more radical, a cosmos where nothing is truly lost, just transformed, recycled, or reborn. Even if they remain mathematical phantoms, they force us to ask deeper questions. Is destruction always permanent? Could the universe have a built-in reset button? The answers might lie not in what we can see, but in what the equations whisper when we dare to follow them all the way to their most unsettling conclusions. What if everything you remember, every person you've loved, every sunset you've watched, every thought you've ever had wasn't real? What if you were just a flicker of self-awareness, conjured into existence for a split second by the random jostling of atoms in the void? This is the nightmare scenario of the Boltzmann brain, a thought experiment so unsettling it keeps physicists awake at night. Named after 19th century scientist Ludwig Boltzmann, who wrestled with the statistical nature of reality, the idea goes like this. In an infinite universe where time stretches endlessly forward, even the most improbable events must happen eventually. Given enough eons, particles floating in the cold, empty darkness could spontaneously arrange themselves into a fully formed, conscious brain, complete with false memories of an entire life that never actually happened. And here's the kicker: statistically speaking, such fleeting illusions should outnumber real, biological minds like yours by an unimaginable margin. The paradox cuts to the heart of cosmology's biggest questions. If the universe truly lasts forever, then randomness alone guarantees that something will momentarily mimic order. A single, disembodied brain hallucinating its own existence is far more likely than the painstaking evolution of planets, life, and civilizations over billions of years. It's like shaking a box of Scrabble tiles for eternity. Eventually, they'll spell out Hamlet, but they'll also produce countless near misses and nonsensical phrases along the way. The Boltzmann brain is one of those near misses, a self-aware accident doomed to dissolve back into chaos the instant it realizes it exists. And if that's true, how could you ever prove you aren't one? Scientists have scrambled to defang this existential horror show. Some argue that the accelerating expansion of the universe will prevent infinite time, making Boltzmann brains impossible. Others suggest our universe's low entropy starting point, the finely tuned order of the Big Bang, acts as a cosmic safeguard, steering reality towards stable structures like galaxies and minds rather than fleeting aberrations. But the problem won't stay buried. Even cutting-edge theories like the multiverse resurrect it, asking, in an infinite sea of parallel realities, aren't most experiences bound to be statistical flukes? Here's the twist: the Boltzmann brain isn't just a puzzle for physicists. It's a mirror held up to the nature of perception itself. Every time you recall a childhood memory or trust the evidence of your senses, you're making a wager that the past was real, that the world outside your skull exists. The thought experiment doesn't just threaten our place in the cosmos, it undermines the very foundation of how we know anything, and yet we live as if it doesn't matter. We sip coffee, argue about the weather, plan for tomorrow, all while balancing on a tightrope of assumptions about reality. Maybe that's the real lesson. Whether we're Boltzmann brains or not, the act of questioning itself is what makes us undeniably, electrifyingly alive. So the next time you feel the sun on your skin or hear laughter in the distance, lean into it. Reality might be an illusion, but the wonder it sparks, that part's unmistakably real. What if you woke up tomorrow and discovered 300 years of history were pure fiction? That's the jaw-dropping claim at the heart of the phantom time hypothesis, a theory so audacious it makes time travelers look tame. In the 1980s, German historian Herbert Illich dropped a bombshell. The early Middle Ages, from roughly 600 to 900 AD, never actually happened. According to him, the years were invented either by accident through faulty record-keeping or deliberately by shadowy powers rewriting the past. If true, it would mean Charlemagne's empire, the Viking Age, even the Islamic Golden Age were elaborate illusions, and the calendar we trust today is off by centuries. Suddenly, the year 2024 might really be 1727. At first glance, the idea seems too wild to take seriously. But Illich and his supporters pointed to eerie gaps in the archaeological record, inconsistencies in ancient solar eclipse reports, and the sudden appearance of Romanesque architecture supposedly built centuries after Rome's fall. How could so much knowledge vanish only to reappear fully formed? To phantom time believers, these weren't mysteries, they were clues to a grand historical cover-up. The theory's critics, of course, weren't convinced. Dendrochronology tree ring dating shows unbroken climate records stretching back thousands of years, and Chinese astronomers documented celestial events that align perfectly with conventional timelines. Yet the phantom time hypothesis lingers not because it's credible, but because it taps into a deeper unease. How much of history is built on sand? Here's where it gets cosmic. If human timelines can be questioned, what about the universes? Astronomers measure the age of stars by their light, the expansion of space by redshift, but these methods rely on assumptions about constants like the speed of light or the uniformity of physics. What if those assumptions are flawed? Could the 14-billion-year history of the cosmos be a kind of collective illusion, a story we've pieced together from fragments we don't fully understand? The phantom time hypothesis might be a historical dead end, but it's also a mirror. It forces us to confront how much we take on faith, whether we're reading a medieval chronicle or a telescope's data. The past isn't just a sequence of events, it's a narrative we construct, a fragile bridge between what we know and what we've lost. And whether we're talking about phantom centuries or the birth of galaxies, the same question haunts us: how do we tell the difference between the story and the truth? Maybe the real lesson isn't that history can be faked, but that every timeline, cosmic or human, is an act of trust. And sometimes the most valuable discoveries begin with asking, what if we're wrong? What if the universe isn't just governed by physics, but by physics engines? The simulation argument, thrust into the mainstream by figures like Elon Musk, suggests our reality might not be the base layer at all. Instead, we could be living inside an unfathomably advanced computer simulation, our lives and laws of nature mere lines of code written by some distant civilization. It sounds like sci-fi, but the idea has roots stretching back millennia. Plato's allegory of the cave, where prisoners mistake shadows on a wall for reality, was an ancient prelude to this modern dilemma. The core question is the same: how do we know what's really real? The argument gains traction from eerie parallels between our universe and a well-crafted simulation. Think about pixels on a screen, tiny, discrete units that blend seamlessly into images. Now replace pixels with Planck lengths, the smallest measurable units of space. Or consider how video games render only what players see to save processing power. Isn't it odd that quantum particles exist in fuzzy probability states until observed, almost like a simulation optimizing resources by calculating outcomes only when needed? Even the speed of light could be seen as a built-in processing limit, a cosmic frame rate preventing the system from overloading. Skeptics, of course, have counterpoints. If we're in a simulation, where are the glitches? Where's the equivalent of a programmer accidentally dropping a coffee cup into their virtual world? Some argue that the sheer complexity of simulating every atom in a universe would be too energy-intensive, even for a hyper-advanced civilization. But simulation theorists fire back. What if the creators only think they're simulating a universe while actually existing in a simulation themselves? It's turtles all the way down a dizzying recursion of realities within realities. The debate isn't just philosophical fluff, it has tangible stakes. If we're living in code, does morality change? Do simulated lives matter less? And if there's even a 1% chance the theory's true, shouldn't we prioritize research to detect potential artifacts in the fabric of reality, anomalies that betray our programmed nature? Some scientists have seriously proposed experiments, like hunting for geometric patterns in cosmic rays or testing whether quantum randomness shows signs of computational shortcuts. Here's the twist: whether the simulation hypothesis is true or not, it's already reshaping how we see existence. It forces us to confront the unsettling possibility that our deepest truths, love, pain, the taste of rain, might be secondary to some higher layer of logic we can't perceive. But maybe that's the point. Real or simulated, the wonder we feel staring at the stars or holding a loved one's hand doesn't diminish. If anything, the universe becomes even more astonishing, not because it's fake, but because it feels so real. And in that feeling, we might find the only answer that truly matters. Imagine living your life over and over, not just once, but an infinite number of times, with every joy and sorrow repeating exactly as before. This isn't the plot of a dystopian novel. It's the heart of Friedrich Nietzsche's Eternal Return, a philosophical sledgehammer meant to test how deeply we value our existence. Nietzsche framed it as a thought experiment. If a demon whispered that every moment of your life, down to the smallest detail, would recur eternally, would you despair or embrace it as divine? But the German philosopher wasn't the first to ponder cyclical time. Centuries earlier, the Mayans meticulously charted vast cosmic cycles where worlds were destroyed and reborn, while Hindu scriptures describe the universe breathing in and out across epochs of creation and dissolution called kalpas. These weren't metaphors, they were maps of reality itself, woven into calendars and sacred texts with mathematical precision. What's astonishing isn't just the persistence of this idea across cultures, it's how modern physics leaves room for it. Einstein's equations allow for closed time-like curves, theoretical loops where time circles back on itself. Some interpretations of quantum mechanics suggest the universe could reset at the Big Crunch, the hypothetical collapse that might follow expansion. Even entropy, the relentless march toward disorder, might not be the final word. In an infinite universe with finite possible states, statistical inevitability suggests arrangements of matter could eventually repeat, like a deck of cards shuffled back to its original order. The implications are dizzying. Every conversation you've had, every star that's ever burned, could it all be trapped in an endless rerun? But here's the twist: cyclical time challenges more than our clocks. It unravels our deepest notions of progress and meaning. Western thought leans linear history as an arrow, science as a scent, life as a journey toward some end. The Eternal Return upends that. If everything recurs, then every choice is both fleeting and eternal, every action weighted with infinite consequence. Nietzsche's real question wasn't about cosmology, it was about courage. Could you look at your life and say, again, please, science hasn't confirmed or ruled out the possibility? The cosmic microwave background shows no evidence of prior cycles, but some versions of string theory posit colliding brain worlds that could birth new universes in an endless cycle. The Mayans might have been closer than we think, yet the theory's power lies beyond proof. It's a mirror. Whether time is a line, a circle, or something stranger, the real mystery isn't the universe's structure, but how we choose to fill the moments we're given. After all, if today's mistakes and triumphs might echo forever, perhaps the only sane response is to live like it's true, not out of fear, but as an invitation to make each iteration count. The idea that consciousness might spring from the quantum realm sounds like something ripped from a sci-fi novel, yet some of the brightest minds in physics and neuroscience have seriously considered it. At the heart of this theory lies a radical proposition. What if the strange, probabilistic behavior of particles at the quantum level isn't confined to labs and particle colliders? What if it's happening right now inside your brain, shaping every thought and sensation? The notion gained traction when physicist Roger Penrose teamed up with anesthesiologist Stuart Hameroff in the 1990s, suggesting that tiny structures called microtubules within neurons could harness quantum effects to generate consciousness. Picture these microscopic tubes as quantum computers, processing information in superposition where particles exist in multiple states at once, until collapsing into a single experience, moment by moment. Critics pounce on the idea with legitimate skepticism. Quantum states are notoriously fragile, requiring extreme cold and isolation to avoid decoherence, where outside noise destroys delicate superpositions. How could such phenomena survive the warm, wet chaos of the human brain? Yet defenders counter with examples like photosynthesis, where quantum coherence plays a role in efficient energy transfer, even in biological systems. And then there's the observer effect in quantum mechanics, where the act of measurement seems to influence the state of a particle. If consciousness arises from quantum processes, could our very awareness be what crystallizes fuzzy probabilities into concrete reality? It's a dizzying loop, the observer shaping the observed, while the observed gives rise to the observer. Philosophers have long wrestled with the hard problem of consciousness, why subjective experience exists at all. The quantum angle offers a tantalizing bridge between the objective world of physics and the inner world of feeling, but it also raises wilder possibilities. Could focused intention, like meditation or collective belief, subtly nudge quantum outcomes? Some interpretations of the double-slit experiment suggest particles know when they're being watched, changing behavior accordingly. While mainstream science dismisses this as metaphorical, the line between measurement and mind remains provocatively blurry. The theory's real power isn't in its answers, it's in the questions it forces us to confront. If quantum consciousness holds even a sliver of truth, reality might be far more participatory than we ever imagined. Not just a universe we observe, but one we're entangled with moment by moment, thought by thought. Whether the idea survives future experiments or fades into obscurity, it's already reshaped the dialogue between science and spirituality, proving that the deepest mysteries often lie at the intersections between the measurable and the felt, the particle and the mind. And perhaps that's where the next breakthrough will emerge, not in choosing between physics and philosophy, but in daring to explore where they collide. The universe might not have the depth we think it does literally. The holographic principle turns our understanding of reality inside out, suggesting that everything we perceive in three glorious dimensions, every star, every planet, even the chair you're sitting on, could be nothing more than a projection from a two-dimensional surface at the edge of space. Picture a hologram on your credit card, flat under the light yet shimmering with illusory depth. Now imagine that, but on the scale of the cosmos. This isn't science fiction. It's a serious, if speculative, theory born from the most enigmatic objects in existence, black holes. The idea first took shape in the 1990s when physicists Gerard T. Hooft and Leonard Susskind wrestled with a paradox. Black holes, they realized, destroy information, something quantum mechanics strictly forbids. But if the information swallowed by a black hole wasn't lost, just encoded on its event horizon like data on a cosmic hard drive, the paradox vanished. From there, the leap was staggering. If a black hole's surface could hold all the information about what fell inside, could the entire universe work the same way? Suddenly, the three-dimensional world might be a kind of shadow, a grand illusion cast from a vast, flat boundary we can't see. Here's where it gets even stranger. The mathematics behind the holographic principle don't just suggest that reality is a projection. They imply that space itself is pixelated, built from tiny, indivisible units of information. Think of your computer screen. Up close, it's just colored dots, but from a distance, they blend into a seamless image. If the universe operates similarly, then what we call empty space could be buzzing with hidden code, a cosmic operating system running the simulation we call existence. This isn't just abstract theorizing. Experiments like the holometer at Fermilab have hunted for evidence of this pixelation, searching for faint jitters in spacetime that might betray its digital-like structure. So far, no smoking gun, but the search reshapes how we think about the fabric of reality. Critics argue that the holographic principle, while mathematically elegant, lacks direct proof. After all, how do you test whether the world around you is fundamentally flat? Yet the theory's allure lies in its audacity. It forces us to confront the possibility that our sensory experience, the solidity of objects, the vastness of the sky, might be a trick of scale, like an ant mistaking a painted mural for an actual landscape. And if true, it would mean that the universe's true nature isn't in the stars or the void between them, but on a distant, invisible surface where all information is stored, waiting to be decoded. Whether the holographic principle holds up or not, it's already done something remarkable, blurred the line between physics and philosophy. If reality is a kind of cosmic sleight of hand, what does that say about free will, about consciousness, about the nature of existence itself? The theory doesn't just challenge our models of the universe, it challenges our place within it. And perhaps that's the real lesson here. Sometimes the most radical ideas aren't just about answering questions, but about learning how to ask them in entirely new ways. After all, if the universe is a hologram, then the greatest mystery isn't what we see, it's what's casting the shadow. From cosmic eggs to holograms, these 25 forgotten theories aren't just footnotes in history. They're proof that the universe refuses to fit neatly into the boxes we build for it. Every era's obvious truths were once someone else's wild speculation, and every breakthrough began with a question too bold to ignore. Think about it, without the dreamers who dared to imagine hollow planets or electrified galaxies, would we have ever probed Earth's core or mapped the magnetic webs of galaxy clusters? Wrong answers aren't dead ends, they're signposts pointing toward deeper mysteries. Consider how many of these ideas started as laughable heresies. The Big Bang was once dismissed as metaphysical nonsense. Black holes were mathematical ghosts even Einstein doubted. Today, they're pillars of modern cosmology. That's the real magic of science. It's not a straight path to truth, but a sprawling, chaotic conversation where even the loudest wrong turns help us find our way. The theories we've explored weren't failures. They were stepping stones, each one stretching the boundaries of what seemed possible. So what's next? Right now, labs are testing ideas that might seem just as outlandish. Parallel universes, time crystals, even consciousness as a fundamental force of nature. Some will fade into obscurity, others might rewrite the textbooks, but here's the beautiful part: we don't have to guess which is which. The cosmos reveals itself to those willing to ask, test, and when the evidence demands it, let go of even the most cherished assumptions. That's how progress happens, not by clinging to comfort, but by embracing the thrilling uncertainty of the unknown. As you scroll through the comments to share which theory hooked you, whether it's Zwicky's tired light or the eerie Boltzmann brains, remember this: the next great revolution in science might be hiding in plain sight, waiting for someone to connect the dots in a way no one else has dared. So stay curious, stay skeptical, and above all, keep wondering. After all, today's crazy idea could be tomorrow's reality. And if history's taught us anything, it's that the universe always has one more surprise up its sleeve. Don't miss the next chapter, hit subscribe, and let's keep unraveling the cosmos together. The best discoveries aren't behind us, they're waiting just beyond the edge of what we think we